Yeah, okay, you can go on.
So, good evening, everyone. Welcome to the sixth talk of Sci-Fi. So, today we have Sayan Banik as our speaker. Sayan is my colleague in NISER Bhubaneswar. He did his bachelor from Scottish State College and then he joined NISER for his integrated PhD course. So, currently he is working under Dr. Subhankar Vedanta. So the topic of the talk is emergence of novel spin textures in magnetic thin films and their applications. So one thing I want to mention that the question answer session of the talk will come at the end of the talk. So do type your questions in the chat box or raise your hand and I will come one by one. So over to you, sir.
Okay, yeah, it will be fine if the questions are asked in the end of the talk.
Yes, yes. The questions will
Okay,
be asked at the end of the talk.
okay.
So you can start.
So, so thank you, Shidipto, for the introduction. Now, today's talk, I will discuss about the origin of different spin textures in magnetic thin film and their application. Now, magnetic thin film means one layer of atoms in a plane. It's a 2D material of thickness angstrom order. Now, this is my overview of talk. First, I will discuss about the introduction, that is the magnetic interaction and the skyrmion. This is the most important spin textures in magnets. And then I will discuss the different kind of Hall effects. And then I will discuss why the skyrmions are so much important in our modern technologies. Then I will discuss that how we can detect a skyrmion in magnetic thin films experimentally. Then I will discuss how the skyrmions are manipulated. That is how we can use them or implement them in our devices. And lastly, the conclusion. So these are several kind of magnetic interaction. Now in this talk, I will discuss the things will be discussed only in case of ferromagnetic materials. So in ferromagnetic materials, each atom has an intrinsic dipole moment. Now there are several magnetic interactions. You see these 5 kind of magnetic interactions that are present in case of magnet or ferromagnet or antiferromagnet. Now the first one is the exchange interaction. It is a short range interaction and the interaction between two spins of atom, two neighboring spins of atom. Now this is the Hamiltonian due to exchange interaction. This J is called the exchange coupling, or rather the stiffness coupling constant. Now SI vector is the spin on the ith atom and SJ vector is the spin on the jth atom. So this is the exchange interaction, and you can see that the exchange interaction favors the parallel spin alignment to minimize its energy. Now the second one is the dipolar interaction. Now as at each atom we have intrinsic dipole moments, so it's obvious that the two dipole will interact to each other, and this interaction favors the anti-parallel alignment of spins. Now second one is the uniaxial anisotropy. Now uniaxial anisotropy, due to uniaxial anisotropy, there comes a special direction in our magnetic system along which the spins try to point in that direction. Now here J cap is the preferred direction of spin alignment. This anisotropy, this type of anisotropy comes in the system due to disorder present in the system. And due to that disorder, this Hamiltonian comes, which tries to make the spins point along the uniaxial anisotropy direction. Now the third one is the Zhylesinski-Muria interaction. This is or DMI. I will call it as DMI. Now the DMI is you can see that this is the cross product term, that is SI vector cross SJ vector. Now the Zhylesinski-Muria interaction term originates in a system due to the breaking of inversion symmetry. When you have inversion symmetry, the environment at plus R vector will be exactly equal to that of minus R vector. Now you see that when you perform the cross product SI vector cross SJ vector at plus R vector, that will be exactly equal and opposite to that performed at minus R vector. So the two effect will combine and cancel the DMI term when we have inversion symmetry. in our magnetic system. So to survive that term, we must break the symmetry, inversion symmetry in our system. The fifth one is the Zeeman interaction, and this is the interaction of the magnetic dipole moments with the externally applied magnetic field. So these are the 5 kind of magnetic interactions present, and there is a variation of the strength of each interactions from material to material, and it depends completely on the position of the metal in periodic table. For example, in case of iron, the Fe, we all know in Fe the exchange interaction and the dipolar interaction is the most dominant one over these two type of interaction. For exchange interaction, which favors the parallel spin of alignment, we get the domains for exchange interaction. Now, when we go beyond our domains, that is, we accommodate more and more atoms or rather spins or dipole moment, the dipolar interaction becomes substantial, and the energy minimized by the dipolar interaction becomes more than the energy minimized by the exchange interaction, and in that case, the spin flipping will occur. Now, this spin flipping gives us the domain wall. So these two terms together gives us domain and domain wall in case of iron, what we know. But in general, let's see what are the consequences of those magnetic structures, magnetic interactions. So you see in the left image, the small dots you can see, these are the atoms, and the arrows are the dipole moment of those atoms. So you start from this position, you can start from this spin. You can see the spin, the alignment of the dipole of the next neighbor. The exchange interaction tries to make it parallel, and the Zyloshinsky-Modian interaction tries to make it perpendicular, and you can see the both effect present in the case. Here I have taken only the exchange interaction and DMI interaction, and this is the strength of the interaction. The J means the strength of exchange interaction, and D means the strength of the Zyloshinsky-Modian interaction. Now if you move across the line, you can see their effect. Now you see the angle made by the second spin with the first spin, the angle continuously rotates. The theta, if you map the theta into a circle, you will see from going here to here, one complete rotation of theta, 2 pi rotation of theta is done. Now that 2 pi rotation of theta corresponds to one topological charge. Now this type of structure is called soliton. This is a 1D structure. Now you come to the 2D case. This is the 2D case of this one. Now if you move across any direction in the thin film, you will see that the magnetic moment vector will rotate around a particular axis in a disciplined order. This is called a spin spiral state, and this is the most general state in case of ferromagnets we have. Now from these states, these are the topological textures made artificially or rather experimentally, which originates from the spin spiral state. As I said that this is a general state. Now if you play with those 4 or 5 interaction terms in this system, you will get these kinds of different structures of the dipole angle of the dipole moment. Now each structure corresponds to a particular value of each magnetic interactions, and those magnetic interactions you can change in your system by introducing disorder or by applying electric field or magnetic field. That is, you have to change the magnetization in the sample, and by changing the magnetization you will get this type of different textures. You see that the spins are in this fashion. This type of texture is called vortex. This type of texture is called flower, and this type of texture is called stripe. Now in this talk, the vortex and the stripe will be more important. Now there is another texture in their family, which is the most important one, the skyrmions. Now skyrmions is actually the is actually the swirling of the spins in a magnetic thin film. Now you see this type of structure. This type of structure is called skyrmions. Now, if you go from one side to another side along any diameter, you will see the rotation of the angle theta in this manner. You see that the theta here makes a one complete 2 pi rotation in skyrmion. That's why the skyrmion corresponds to a topological charge 1. Now, in this theta, in this case, the theta rotates in clockwise direction, and the clockwise direction means the topological charge, the q is equal to +1. The skyrmion with topological charge +1 is called achiral skyrmion, and the rotation can be in different direction, that is the anti-clockwise direction, and that will be topological charge q is equal to -1, and that is called chiral skyrmion. And now you see that this is the magnetic thin film. This is the 3D picture of this. You can see that there is a confined region in which this structure is found, and rest of the regions, the spin, the atomic moments in the rest of the regions are exactly parallel to each other. This state in magnetic material is called a skyrmionic state, and the skyrmions is the most important thing among all the textures, because skyrmion is more stable than any other texture, and it has particle-like properties which can be used for information carriers in modern technologies. And also skyrmion have several substructures which can be used simultaneously in a magnetic system, and to access those substructures we have not to play with those kind of interactions in our system. So the skyrmions. Now I will discuss the different kind of Hall effects those are present in the magnetic system. Now, first of all, the anomalous Hall effect. See, we all know the ordinary Hall effect is proportional to the applied magnetic field, but in case of ferromagnet, it was found that the transverse resistivity is proportional to the magnetization, and that's why it was called the anomalous one. Now there are three reasons for the anomalous Hall effect. The first one is the skew scattering of the electrons due to the impurities present in our system. This is similarly just like similar to the Rutherford scattering, the first one, and the second one is the sudden shift of electron in its motion, sudden shift of electron coordinates in its motion, which is called the side jump mechanism. Now the 1 and 2 occurs due to the spin orbit coupling. When you have no spin orbit coupling in your system, the 1 and 2 will not occur. Now the 1 and 2 mechanism gives us the anomalous velocity component, sorry, extra velocity component, which is called anomalous velocity component. Okay. Now if you add those anomalous velocity for each electrons residing in several bands in the ferromagnet, it will give you a non-zero component of velocity. The exactly same that was given by the Lorentz force in case of ordinary Hall effect. Now in case of ferromagnetic material, we have anomalous velocity component which contributes to the total resistivity curve as the anomalous Hall effect. Now the third one is different from them. The third one, the Berry phase. Now what is the Berry phase? When an electron is subjected to a specific Hamiltonian, time-dependent Hamiltonian, a geometrical phase will be introduced into the wave function of that electron along with the dynamical phase, the e to the power I t over h cross. So this phase is called Berry phase. Now it will be seen later that the electrons in ferromagnet are encountered with a special kind of Hamiltonian in which more than one parameter changes with time, and this induces the geometrical phase called Berry phase. And a detailed theoretical calculation shows us that in case of ferromagnets, this geometrical phase, or rather the Berry phase, gives us a component, gives us a new type of resistivity, and that resistivity is proportional to the magnetization in case of ferromagnetic material. So it was included into the anomalous Hall family. So these are the three types of reasons why we have the resistivity proportional to the magnetization. Now the second one is the topological Hall effect. Now you see this is the three spins of atom taken from a spin spiral state, three neighboring spins. I showed you the spin spiral state before. Now you take any three neighboring spins from any place and bring them to the center of a circle without changing the direction. It's their direction of the spins. Now you will see that they will form this kind of structure. And if you look at this scalar product, you will see that this is actually the solid angle subtended by these three spins. Now a Hall effect, that is a contribution to the total Hall resistivity due to different reason as that of anomalous Hall effect, is proportional to the this spin chirality, that is SI vector dot SJ vector cross SK vector. Now look at this formula. You see, this is the n of r is the SR vector, that is divided by mod SR vector. You see that when we have a variation of the spin direction, the spatial variation of the spin direction in our system, we will get a non-zero value of B effective field. Now this B effective field is completely intrinsic, or rather it is called the intrinsic magnetic field. Now the obviously the magnetic field will contribute to the resistivity with the resistivity as the topological Hall effect. Now you see that the rho THE, that is the resistivity due to the topological Hall effect, is proportional to the RT into B effective. RT is called the anomalous Hall coefficient, and this is the total resistivity we have. The R0H is due to the ordinary Hall effect. This is proportional to the M due to the anomalous Hall effect, and this is due to the topological Hall effect. Now you see this graph. Yeah, you see the yellow line. The yellow line is due to the anomalous Hall effect, and as I said earlier that it is proportional to the magnetization. It will obviously show hysteresis type loop when varied with the magnetic field. Now the blue curve is due to the topological Hall effect. Now why its nature is just like this? See, when we are at zero magnetic field, we have a spin spiral state. As I told you that it is the most general state. We have spin spiral state. Now when I increase the magnetic field, the spins in the atomic moments in the magnetic thin film starts pointing in the direction of the applied magnetic field. And in the case at this point where the topological Hall effect, or rather the spin chirality, is maximum, in this point we have a skyrmionic state. This state, you see, the most of the spins, most of the moments of the material has been aligned to the magnetic field direction, which is in this case is along the Z direction, and there is a small region in which we cannot see the effect of magnetic field, or it has not affected by the magnetic field, applied magnetic field. And this type of feature will create a skyrmionic state, and that's why the topological Hall effect, or rather the spin chirality, will be maximum in the skyrmionic state, and it will not be maximum in the spin spiral state, because there will be some negative contribution to this product. And now when you increase the applied magnetic field further, that is the strength of the magnetic field becomes so much, you will enter into the saturation region. That is, all your spins, all your the magnetic moments will be directed along the magnetic field, and there will be these spins will be parallel to each other, and there will be no, the solid angle will be 0, and there will be no spin chirality. The topological Hall effect will go to 0. Now the red one, you see, this is the combined effect of the blue curve and the yellow curve. You can see this is the total resistivity curve, and you can see there is a bulge and there is a dent in there. This type of this type of behavior is called Hall anomalies in our system. Now, why the skyrmions are so important to us? You see the left triangle. This is the current memory system we are using nowadays, and below the triangle, you see this is the storage device these are the storage device which we use, the hard disks and the solid state drive we use. And in the middle we have the random access memory family, the SRAM and DRAM, and these are volatile. Now SRAM uses flip-flops and DRAM uses some capacitor and transistor. When the capacitor is fully charged, it is called 1, and when the capacitor is fully discharged, it is called 0. These are the bits, and they are maintained by the transistor. So in this case, you see that we have to play with energies, and in that game, some amount of energy will be lost, and we will have heat. We will have heat in those systems. Now you come to the future memory. These these are under research now. Now we can use the racetrack memory, which is based on the domain wall motion. This racetrack memory can be used as a mass storage device. That is, it can supplement the SSDs and the hard disks. Till now, IBM has developed a racetrack memory which can store only 3 bits, but the research is going on. In the middle, this is the memory systems built by spintronic memory. Spintronics. Now, you see, in electronics, we deal with the charge of an electron and the motion of an electron according to the voltage difference. Spintronic deals with the spin of electrons and the motion of electrons according to its 2 different polarization states. Now, the research branch which deals only skyrmionics is a sub part of the spintronics. The research area of spintronics is vast. So the memories, that is the RAM made by this skyrmionic or rather the spintronic memories by the spintronic system will be firstly, it will be non-volatile in nature, and secondly, it will dissipate less heat. There will be less heating issues because there are no physical motion of electrons, and we have not to store or rather play with energies in this case. Rather, this type of memories can contain more information. That is, the bit densities are higher in this case. Now, the experimental detection of skyrmions, that is how we will know the skyrmions can be, that we have a skyrmion in our system. See, we have to perform our measurements in materials, and the materials are drawn in our lab experimentally, and this is done on the substrate, on a substrate. Now, the substrate gives the crystalline growth of our material. That material, that is the thin film. Without the substrate, the growth of the thin film will be amorphous in nature. So here we are using the strontium luthanate oxide, that is SRO, thin film, as our interested material, and the strontium titanium oxide as the substrate. So this a magnetic field is applied along the thin film, and you can see the results. The y-axis corresponds to the resistivity, and the x-axis to the magnetic field, and each column corresponds to the different thickness of the material, that is the SRO film, different thickness or SRO film of the SRO film. And these different graphs are at different temperatures. Suppose at T is equal to 5 nanometer, this is for 40 Kelvin, and the blue is for 80 Kelvin. Now you can see that in this measurement, when the thickness of the nanometer is 5, thickness of the thin film is 5 nanometer, and the applied magnetic field is somewhat near 5 kilo state, there are Hall anomalies. Previously, we have shown in the graph that these Hall anomalies corresponds to the skyrmionic state. Here the skyrmion will be with topological charge +1, and here the skyrmion will be with topological charge -1. So we can, from this data, we can ensure that at the temperature near 60 Kelvin and the magnetic field of 5 kilo state and thickness T is equal to 5 nanometer, we will have this kind of Hall anomalies and the skyrmionic state in the strontium luthanate oxide. That's why, that's how in experiment the skyrmions are detected. Now, this is the most important part of the talk, the manipulation of the skyrmion. First, look at this figure. This is the thin film, and we are using this material as our thin film. This is the platinum, cobalt, and this is the tantalum. The platinum over cobalt over tantalum. Now, the platinum, cobalt, and tantalum together, this is called one stack. Now, n is the repetition number of that stack. For example, you see there is a 12. That is, there are 12 stack of platinum, cobalt, tantalum kept on each other. So we will be using this platinum, cobalt, tantalum as our thin film, and you can see the top view of our thin film. It is not a continuous thin film as we have in previously here. Rather, there are cylindrical shape. These of the diameter is 350 nanometer. These are called nanodots. Now, this is a ferromagnetic material. Now, the substrate. For the substrate, we use this type of material. The Mg 1/3 and Nb 2/3 means when you have a 1 gram of MgNb, that is the magnesium niobium, in the 1 gram, 1/3 will be magnesium and 2/3 will be niobium. Now 0.7 means that there are 70% Pb Mg 1/3, Nb 2/3, O3, and 30% Pb TiO3. We are using this as our substrate. This is called the PMNPT. Each letter from first letter from each element. Now the PMNPT, we are using the substrate as a ferroelectric material here. Now ferro means magnetic and electric means electrical property. That is a material in which we have both magnetic and electrical properties. And in case of ferroelectric material, if we apply electric field, we will get a magnetization. And if we apply a magnetic field, we will get an electrical signal. So just like piezoelectric crystals. So what is the aim here is we use the tantalum layer and the Au layer as our electrodes, and we apply electric field or electric field pulse in the ferroelectric material. Now, when we apply the electric field or pulse in the ferroelectric material, a strain will be generated in the material, and that strain will modify the magnetization of that material. That magnetization will go to the top layer of our material, and the magnetization of the top layer will be changed due to the change in the magnetization of the second layer, because these two are attached by the interface. Now, when the magnetization of the top layer gets changed, the 5 interaction terms which I told you earlier, the strength of the 5 interaction terms will be modified, and for each we will get different type of textures for different type of magnetization. Now you see this graph. When platinum, cobalt, tantalum is made, this type of thin film is made. Initially, we will have a striped domain. Okay, the striped domain. Now, when we apply a electric pulse of nearly 4 kilovolt of 1 millisecond width, the stripe texture will go to skyrmionic texture by the strain. This is the tensile strain, the skyrmionic texture. Now, when we again apply 10 kilovolt pulse, the skyrmionic texture will go to the vortex texture. Now, when you reduce, when you apply a zero field, the vortex will be retained, and at -4 kilovolt pulse, the vortex will go to the skyrmionic state and stripe state. Now you see that in this case we have to apply only a small magnetic pulse, and once you have applied the magnetic pulse, the magnetic state remains in its position forever. And secondly, we have the switching between those three textures, that is the stripe, skyrmion, and vortex. Those three, the switching between those three textures are completely random. That is, we can go from skyrmionic state to the stripe state, or the stripe state to the vortex state. Randomly we can access those. So in this case, we have three characteristics. Number one, the randomness, and number two is the non-volatility. Non-volatility, that I told you that only a electric pulse will keep it in its position. It will not change. So these two features, the randomness and the non-volatility, enables us to use it as random access memory. See, this is the top layer of the this thin film, the top layer of the thin film. So these nanodots, I told you that the diameter is 350 nanometer. It is kept at 350 nanometer because at this specification, each nanodot contains only one type of the magnetic texture, that is one skyrmion, one vortex. Okay, so in these nanodots we can apply a electric field pulse, and can get, suppose we have got a vortex state. Now from vortex state we can go to the skyrmionic state by applying a -3 kV pulse only, and from skyrmionic state we can go to the stripe state by -10 kilovolt pulse only. Now there we have here we have three types of textures. Now you take any of them, any two among them as 0 and 1. Now 0 and 1 will be our bits. Now this is how you will write the data in your RAM by applying a pulse. Suppose this is your 0 state, you give a -3 kV pulse, it will go to your 1 state, and it is your 1 state, you apply a 10 kV pulse, you will come to your 0 state. That is how writing process can be done in the RAM. Now the reading process. For reading process, we will use a device which changes its resistance when it is kept in different magnetic field. This type of phenomena is called magnetoresistance, the resistance which varies with a magnetic field. This type of junctions is this type of devices is called the magnetic tunnel junction. So if you see, I have showed you the formula before. The magnetic field formula, the magnetic field will depends on the orientation of the spin. So the magnetic field will be different for three different cases. The intrinsic magnetic field I am talking about. So that intrinsic magnetic field will be determined by magnetic tunnel junction. By the change in the resistance, you can detect the change in the magnetic field, and you can program your computer that it will detect the 0 by its magnetic field, and it will detect 1 by its magnetic field. So that's how you can build a random access memory. Now you see that in this case we have no need to no need of electron motion, and no need to store any kind of energy. Or rather, the switching process between these two states is very fast than the discharging time of the transistors. So so these are very cheap in market, the magnetic materials. We need only a magnetic material, so these are very cheap materials, and one electric pulse is enough to keep it in the state. So by this process we will have a non-volatile RAM which is more efficient, which is the energy efficient, more fast and more cheaper than the DDR generations we are using right now. One more thing, the densities of these nanodots, we can make higher density of this nanodot, such that these nanodots contain the RAM made by this technology can contain 1 GB RAM made by this technology can contain more data than 1 GB RAM made by the today's technology. So one more thing, in this case we have the skyrmion with topological charge +1 and skyrmion with charge of topological charge -1. Now you can ask that we can use this as 0 and 1. Now we cannot use this like that. First of all, you see that to retain the skyrmionic state, we have to keep on applying the magnetic field. That destroys the non-volatile feature in this type of experiment. And secondly, in going from the charge +1, q is equal to +1 to q is equal to -1, the several in this region, several different types of textures will be arise, and those cannot be accessed randomly. So they are this feature also kills the randomness of the thing. So we cannot use this technology, that is technology by applying magnetic field as to make the RAM. So in the conclusion, we have seen that in case of strontium glutamate oxide, we have the skyrmions. We have the topological Hall effect, and the topological Hall effect is the hallmark of the skyrmion. And we have realized the electric field induced switching of the electric field induced switching of the skyrmions in the ferromagnetic by ferroelectric heterostructure. Now, skyrmions can be also used to build AND OR gates. And the gates, the basic gates made by the skyrmions will be more efficient than today's one, and this will simplify our digital circuits. Secondly, the skyrmions are also used in medical science devices. For example, the skyrmions are used in some artificial neuron type devices, and there are a lot more. These are the importance of skyrmions. The importance of spintronics is more vast than the skyrmions. So lastly, all these things I have told is in case of ferromagnet. We can get this type of features in antiferromagnets also, but in antiferromagnetic case, it holds many things, and it is far from experimental implementation. Till now, basic kind of experiments are going in with antiferromagnetic cases, and that's one. Thank you.
Okay. So thank you, Sayan. That was a wonderful talk. So now comes the question and answer session. So if you have any question, you can type in the chat box or raise your hand. Okay. So I can see one question from Krishnendu Maji.
Shudipta, you can do one thing. You can also allow the people who ask their question in a chat box to unmute themselves and ask the question directly if they want to.
Sorry.
You can also allow the people who have written the question in a chat box to unmute themselves if they want to.
Okay. So Krishnendu, do you want to ask question, or I will read it out?
Yeah. Then okay, I am reading.
Okay.
I am telling you directly. Okay. So my question is that what kind of interaction are mainly responsible for the Skyrmion state? You are asking for.
The mainly interaction responsible for is the Zhailoshinsky-Moria interaction term and the exchange interaction term. And in thin film, the anisotropy term is mostly is not present there, but these are two effective steps.
Okay, okay. And what kind of competition between these two terms allows, if we that determine that am I going to get vortex state or
well, you have to look into it experimentally. The combination you are telling about is different for different types of material. Okay, and the main thing is that there are no methods to measure the strength of this kind of interactions. Okay, so you have to go by changing your external parameters. Okay, that depends upon the experience on your experimental techniques.
There is no Hamiltonian the form. There is no Hamiltonian to. I think the toy model. Any toy model is there is to check.
Yes. The Hamiltonian contains those all terms, but it depends which term will be more dominant over which term. The Hamiltonian is always this is if you include this 5 kind of Hamiltonian summation. The total Hamiltonian is called the Heisenberg Hamiltonian in case of magnetic materials. It contains these 5 terms.
Okay.
Okay. So
Thank you.
I can see one question from Doipayan. So
Yeah.
Doipayan,
Yeah. Thanks,
you can-
Shudipto. Okay. Am I audible?
Yes.
Okay. Yeah, Shayan, thanks for the talk. So I just wanted to ask, so what in your lab you do these experiments, right? So what kind of material do you use to create these fermionic states? That's the first question. Okay.
Till now I have spent very less time in labs, so
Okay.
I have not. So in case of I have shown you that in case of strontium ruthenate oxide, okay, the specification is the 5 nanometer temperature and electric field, and in this specification range we will get a skyrmion. The experiments tells us that. Okay. Now this is the SRO thin film. Now this is recently found, the SRO film. Previously a film called LSMO. The name LSMO is just like this. LSMO is done by this process. Okay. The LSMO, the material. This is SRO, that LSMO material. LSMO material you will find skyrmion in more easily. But it depends that in which material you get all the substrates of the skyrmion. You will not get all the substrates of the skyrmion in every material. So you can make a material by composition of material.
Okay, so my final question is that do you have a number on how fast computation speeds will become compared to the devices that we are using now?
No, see, the thing I told you, it is proposed just 2 months before. Okay, still it's an idea. Still it's an idea, and it goes to the manufacturer, the engineering part to implement it. So they are
so any theoretical idea, maybe a number, maybe you expect this kind of speed or something?
For fastness, no, I have no idea.
Okay, thank you. That's it, Shudipto. Thanks.
Okay. So I cannot see any more questions. So once again, if you have any question, okay, I can see one question from XYZ. So XYZ, you can unmute yourself if you don't have any problem in your mic. Okay, so I think, okay, I will read the question. So he is saying that, hi, I have a question to you. We know that Pauli spin susceptibility becomes independent of temperature in 2D because the spin dependent magnetism, and hence the susceptibility has a non-trivial dependence on the topological arrangement of electrons. So please explain me what is your topological arrangement of electrons.
No, these are not topological arrangement of electrons. These are the topological arrangement of the atomic dipole moments of each atom. There are intrinsic dipole moment in case of ferromagnetic, and the dipole moment comes from in case of iron, it comes from the d orbital, the half filled d orbital. So these are the direction of the atomic dipole moments.
Okay, I hope you understand. So if you have any more question regarding this XYZ, so you can ask in the chat box. I cannot see any more question. Okay, so Sayan, I have few questions.
Shudipto, Shopanno has a question.
Where? Okay. So Sopan have few questions too. So yes, Sopan, you can unmute yourself.
Yeah, thank you, Shudipto. Thank you, Shayan, also for a good talk. First of all, am I audible?
Yes.
So, Shayan, I have a few questions, like just simple ones. So, one is, can you go to this experimental plot where you showed versus this thickness. This versus thickness is your
Yes, yes,
resistivity plot.
yes.
That, yeah. So you see, I'm not sure. We are always observing skyrmions in pair, right? Like topological quanta number 1 and number -1.
Yes,
So,
yes.
so is it just because since it started with the topological quantum number 0, so it has to conserve it. So is it that is the reason that it has to always occur in pairs? Is that the reason?
Uh, Always occur in pair. Yes, for that you can say that. Yes, yes, yes. You can say that because each magnetic each topological charge will correspond to its that is each alignment of the dipole will correspond to a negative alignment of it. Yes, it can be said.
So like yes, exactly. So this was a mathematical statement. I just wanted to know this the physical background. Like as you said that one is chiral and one is anti-chiral. So one is like all rotating in 180 degree and one is all rotating opposite of anti-clockwise. All
Yes,
rotating
anti-clockwise.
one anti-clockwise one. So like I just wanted to know why it is. Like can you give a physical picture, not the mathematical statement like topological quantum number
The
and so on.
physical picture, you can say that, okay. Uh, See, when you have a applied magnetic field, in this case, you are applying a magnetic field in negative direction. Okay. Now, when you are applying it negative direction, obviously, it will go to the negative direction as that of the positive one. So it will align the atomic moments in the negative direction of that in the positive what we get from in the positive region. So that makes one the q is equal to +1, and that is the rotation of theta plus and minus.
Okay, so just because I'm changing the direction of the magnetic field and this change.
Yes, you are changing the because the topological charge originates due to the rotation of the magnetic moment. You have seen that. Now,
Yes.
when you have rotate, they are free to rotate in other direction. There is no restriction in our system.
Okay. So that is what makes it go in the other direction.
Yes.
Okay. It's okay. And one more question. Can you go to the next slide? The
Next slide. This one.
Next slide. This one. So this part actually I lost a bit. So you see this stripe is starting from 0. What is this E average, by the way? The epsilon average on your y-axis?
Oh, sorry. I forgot to tell. E average is the average strain which is generated in the ferroelectric material. Sorry, I forgot to tell it.
Okay. Okay. So when when I started from 0, there was no strain, this type, and then it moved to. So can you give a picture like this one that there was type, then it got strained and it becomes skyrmion, and then finally starts to compress to become vortex. So like what is happening?
You are asking for the
Some kind of
changing background, right?
Yeah. So in applying electric field, first there occurs stress, then there is
Okay.
compression.
Okay, so let me think whether I have anything. See, this type of figure. Okay. See, I cannot show you exactly the conversion between stripe to skyrmion to vortex. Okay, I can show you the topological change in the topological change in the state of skyrmion, the chiral skyrmion and the achiral skyrmion. Okay. So, let's see. Not this one. Yes, you see. First you see the red one is the direction. You see, you take any direction along any direction, and the change in the color is the changing of the direction of the magnetic field. Okay, sorry, that the atomic dipole moment. Okay. Now you can see the switching. You see, there are some regions in which the spins are in red direction. Okay, the blue one is the change in direction. Okay.
Okay. Okay.
Now you see the now at that moment I cannot specify the background of this texture, but this is how they are changed. This is a made by simulation, and
Those isolated red spins are skyrmions. Those
wait,
isolated
just wait a
red.
minute. Yes, you can see there is no variation. You can see this this one. This is actually the change of states. Okay, the change of the dipole moment, direction of the dipole moment. And
Okay. Yes.
I had it previously, but no.
Yeah. Okay.
Okay, have you understood? Because I cannot show you right now. No. Right now, I have not the thing you are wanting.
Okay. Then yeah, sure. Then some other time. We may discuss it later on. Okay. Okay. That's it. Thanks. Thank you.
Okay, so thank you, Soparna. Is there any hand? No. Any question in chat box? Okay, so I can see one question from Saurabh. So Saurabh, you can unmute yourself. Okay, so I will read. Saurabh, are you here? Okay, so I'm reading the question. So he is asking, does skyrmion has analogous model to classical one, or is it solely by quantum spin? If so, is the DM Hamiltonian term putting in phenomenological way or not?
See, the Skyrmion is yes. The DM term, this type of terms, the Zaleshinsky-Moria interaction term and the exchange interaction term, the fundamental origin of these two terms is the spin orbit coupling. When you have you don't have a spin orbit coupling, this term will not be originate. Now the skyrmions itself has the spin is always quantum mechanical, but the skyrmion itself has a particle-like property. That is, we can run the skyrmion in our thin film by experimental technique. So that from that you can say that it has a classical analog with the particle, and that is used in information carrier, as information carriers.
Okay. So, Sopan, do you have any more question, or otherwise you can lower your hand?
Yeah. No. I forgot to lower my hand.
Okay. So I can't see any more hands. See the chat box. No. So Sayan, can I
Yes.
ask some questions? I mean, 2 or 3. Okay. Uh, so can you go to the slide where you have mentioned the topological Hall effect? I mean, there is a graph, hysteresis graph. Yeah. So you can see that the red line
Yes,
curve.
red line.
So there is the 2 branch, and again they are meeting, and again
Yes.
branch, and again meeting. So can you explain it once?
Yes, this is the you are telling that the branch this is
Yes.
that one is coming. There is you see that there is a hysteresis kind of behavior. Okay, so there is this is due to the anomalous Hall effect, but you
Yellow
see
one.
that yes. Oh, you want to you want to know the yellow one?
No, I want to know the red one.
Okay.
Why the branches are come.
Yes, this is the hysteresis kind of loop. That is, if you go from here to here, when you are going from positive direction to negative direction for the first one, for the first time, you will not get this curve. Okay, you will just go to this line, and then it will go to this line, just like this. And but you can see that this for the first time we will not have a skyrmion. Sorry, we will not have any Hall anomalies here. Hall anomalies comes at the second stage, but this nature is due to the anomalous Hall effect. Okay. The topological Hall effect, this type of curve is still there, and you will always get a skyrmionic state. There is nothing to bother with the red one curve. The main thing is the topological Hall effect for the skyrmion one, and you will always get this type of curve.
Okay. Okay. So so I have one more question. So it is basically, so you have said that in this case, I mean, in the case of the spintronics, there is no physical motion of electron. So
yes.
So the heat dissipation is very less, right?
Very less. Yes, very less.
So how the information is traveling in this case?
See, in case of information is traveling. Okay, you see for this you see you have seen the tip of the magnetization. For example, you are sending a spin polarized current. Okay. Suppose there is a wave in which a beam of electron in which all the spins are randomly oriented. Okay. Now you pass it through a system. Okay. Now there will be some differences in the polarization structure of the beam which is coming out of that system. Okay, some plane or some thing will be polarized, and the structure will be different. And if you pass that spin polarized current into your ferromagnetic one, and keep the ferromagnetic material in the magnetic field, you will see that there will be rotation of the these type of these moments around the magnetic field direction. Okay, and this rotation actually, if you see the dynamics of the magnetization, you will get an equation where dm dt is equal to m is equal to the magnetization direction, and dm dt is equal to, there are two terms. Okay, the first term is the torque-like term, which makes the dipole moments rotate, and the second one is the damping-like term, which relaxes the dipole moment to the applied magnetic field. Okay, the tip will be just like the phase space diagram of the damped harmonic oscillator. So within the relaxation time, if you send the spin polarized current or the beam of electron coming out of the system to the ferromagnetic case, the spin polarized current will create a torque on these dipole moments, and from these dipole moments we can decode the planes in which we have polarization. Okay, so that's the idea behind it. Okay, I don't know that in great detail.
Okay.
Okay.
So you are using 2D film. I mean, only one layer of spin.
Yes. One layer of spin, because
as in
yes.
In this picture, in this right.
One layer of films. This is actually Niels skyrmion. This is called a Niels skyrmion. Found only in 2D films. Okay, there is only another type of skyrmion called the block skyrmion, which is found in bulk materials. Now the working with Niels skyrmions is much more efficient.
Okay, so this one is a 2D film.
Yes, this is in.
And just one more clarification I need. So can you go to the slide manipulation of skyrmion? So there was something like Mg, magnesium 1/3. So what does this 1/3, 2/3? Can you explain?
Okay, so suppose you are making the MgNB material. Okay, suppose you have a 1 gram of MgNB material, and in 1 gram of MgNB material, 1/3 will be magnesium and 2/3 will be niobium.
Oh, okay. So these are the ratios.
Yes. The ratios of the.
So ratios by weight or by number, atomic number?
Ratios by atomic number, I think, because This type of materials are made by sputtering. Sputtering means the firing of those atoms into the chamber. So I think these are atomic ratio of.
Okay. 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 So thank you. So is there any more question?
Shuparno, I am sorry that I couldn't clear your question, but right now at this moment I have not the things that I can show you, that the switching of the skyrmions.
Yeah, sure. I mean, once you know, we can discuss it later on sometime.
Yes. Yes. So
No problem.
okay. So I can see one question from Anandram. Anandram A. So you can unmute yourself, or just please wait. 30 seconds. So mic is down. Okay. So he is asking that can you please compare the energy expenditure to encode skyrmions into the material to the technological stance nowadays?
Nowadays, energy. Please read out the question one more time.
So you can see it in the chat box. So he's asking, can you please compare the energy expenditure to encode skyrmions into the material to the technological stance nowadays?
No, till now, see, till now this has not, this technology has not been implemented. So, no, I cannot tell you the exact amount of the energy differences.
Okay, so thank you, Sayan. So, participants engaging hands. Oh, so he's saying something like, isn't 10 kilovolt high? Sayan, can you hear me?
Yes, yes.
So he's saying that, like, isn't it 10 kilovolt high? I mean,
Well,
isn't the
see,
voltage is too high?
in case of platinum, cobalt, tantalum, they have got the 10 kilovolt signal. Okay. Now this is actually the idea. Okay. There is we can make a different type of material, such a material uh, that will use less magnitude pulse. Okay, but in case of platinum, cobalt, tantalum, it is 10. But we can always make complex materials which will use some this less. So that is the future task in implementing this technology.
Okay.
The main thing is we have to change the magnetization. And in case of PMNPT layer, the magnetization change occurs at this particular value. In case of other materials, it may occur at different values. So that may reduce. That is the future task.
Okay. So I can't see any more raising hands or any more questions. So Anandram is saying thank you to you. Okay. So let's thank the speaker for giving this wonderful talk. And Auditro, if you want to make any announcement, then